I'm going to start this video off really going back to like the beginnings of pre-calculus. This is what I tell my pre-calculus students. The one thing I want them to take from pre-calculus are the four formulas that we're about to talk about right here. So the idea being that we've got ourselves a point. This is the point x comma y, but it's also the point r comma theta. Right? We can get there two different ways. We can get there by going horizontally, x units, and vertically, y units, to get to this point. Or we can go r units directly there in the proper direction. And when we create these two different paths, we have four different variables, right? We have x, y, r, and theta, and they're all related. So there are four equations that we can use to relate these. The one that probably everyone learned first is the Pythagorean Theorem, which is the leg squared plus the other leg squared equals the hypotenuse squared. X squared plus y squared equals r squared. So that just relates all of the sides. And then we also have the tangent of theta is equal to y over x, right? That's one of the definitions of the trig functions. Now the other two that I'm going to write, I'm going to start them off using the definitions. The sine of theta equals y over r, and the cosine of theta equals x over r, right? But we don't tend to use them in this form when we're talking about polar. We tend to prefer to solve for x and solve for y. So kind of the idea here is that we've got y equals something in terms of r and theta, and we have x equals something in terms of r and theta as well. So if we have r's and thetas, we can find x's and y's easily. If we have x's and y's, we can find r's and thetas easily, right? So maybe I'll go ahead and finish the pattern here. I'll actually solve for theta here. Theta is equal to the inverse tangent of y over x. Of course, we have to be careful with inverse tangent, right? Because it will only give us answers between negative pi over 2 and positive pi over 2. So quadrant 4 and quadrant 1. If theta is in quadrant 2 or quadrant 3, then we'll have to remember, oh yeah, we have to add pi to this answer to get us into the proper quadrant. And then also, we have, easily enough, we can take the square root of both sides and get x squared plus y squared inside the square root. And we could say plus or minus. We generally will pick positive r values, but as we've seen in those polar graphs, sometimes r's will turn negative, and that's okay as well. So anyway, these are kind of the big conversion equations that we like to use when we're going back and forth between polar and rectangular. So if I have an equation like r equals 4 sine of theta, then we can try to use these conversion equations to get x's and y's in there instead. So this is a little bit non-intuitive, but we don't want to replace r with the square root of x squared plus y squared. We could, but then we're going to get something messy over here. So notice that sine of theta shows up multiplied by r, and that's a nice, easy substitution. So what I would prefer to see over here is not sine of theta, but r times the sine of theta. So what I'm going to do is I'm going to multiply both sides of this equation by r, and that way I'll get r squared equals 4 times r times the sine of theta. All right, so that's not a required step, but it's a really convenient first step, because that way we know that r squared equals x squared plus y squared. So the left side of the equation can just be replaced with x squared plus y squared. And then the r times the sine of theta on the other side can just be replaced with a y. So I suppose you could say we're done. But I would probably prefer to write this in a more standard form. We know this is a circle. We know that circles can be written as x minus h squared plus y minus k squared equals r squared, where h comma k is the center and r is, of course, the radius. So it's probably better if we were to complete the square here. So we'll subtract 4y to the other side. And we'll ask the question, what can we add to this to complete the square? Of course, that's cutting this in half and squaring it. Negative 2 squared is positive 4. We have to keep the equation balanced, so we'll add 4 to the other side as well. And then we can factor, right? We've got x squared, which is already a perfect square, and then this becomes y minus 2 squared when we factor it. And of course, 0 plus 4 is 4. And now we can see that h comma k is 0 comma 2, and the radius is 2. All right, so that's one strategy when you're converting. You might want to multiply both sides by r. Sometimes that's useful. Over here, that would not be a good strategy. If I multiply both sides by r, then I'm going to get r squared equals 4r. And just having a single r is not great. But we do like seeing that r squared. So instead of multiplying both sides by r, let's do a slightly different thing. Let's square both sides. The constant is just a constant, so who cares what it is? We get r squared equals 16, and we know, again, that r squared is the same thing as x squared plus y squared. So we can simply replace the r squared with x squared plus y squared, and there are no squares to complete. We're done. So those are two different conversions from polar to rectangular. From polar to rectangular. Awesome. Now going the other direction tends to be a little less nuanced, right? We don't have to kind of decide what to do. We can just say, well, if I see a y, I'm just going to replace it with r sine of theta. If I see an x, I'm just going to replace it with r cosine theta. And that's really it. So let's pick a new color. Y is the same thing as r times the sine of theta. X is the same thing as r times the cosine of theta. All right, so that's an equation. That's a polar equation. Normally, we like to solve for r. We don't have to. Sometimes it's a little inconvenient to solve for r, but in this case, we can pretty easily solve for r. We've got a 2r cosine theta that we can subtract to the other side. So get all of our r terms on one side, and then if we want to solve for r, we can factor out the r. And then to isolate r, we just divide by the thing we're multiplying by r. So that's going to be negative 3 over sine of theta minus 2 cosine of theta. And that's a fairly complicated looking equation compared to this y equals mx plus b sort of thing. So we can see that lines lend themselves nicely to rectangular form, whereas circles might be a little nicer in polar form. Now, I just want to point out that we could simplify this a bit. I don't really like having all these extra negatives. So if I take that negative out of the numerator and distribute it into the denominator, then our negative 2 becomes a positive 2, and our positive 1 becomes a negative 1. And that's probably a little bit nicer final answer, but they're both correct. All right, now we could do the same thing with this problem. Replace the x with r cosine theta, and we can replace the y with r sine theta, excuse me. But I think I'm going to hold off on that on this one. It just seems like it's going to get a little bit messier than before it gets better. So perhaps I'm going to do all my algebra, or a lot of my algebra at least, in rectangular form first. If I square this out, I get x squared minus 6x plus 9. And if I square this out, I get y squared plus 2y plus 1. And then I might say, well, I like having this x squared and this y squared together. That's something that I've kind of seen before, so I'll kind of keep those together. And then maybe I'll move everything else to the other side. So I've got this minus 6x, so I'll add that 6x to both sides. I've got this plus 2y, so I'll subtract a 2y from both sides. And take a look, I've got a 9 and a 1 that add up to 10. And if I subtract 10 from both sides, then my constants are gone, which is very nice. So this is going to be a much simpler equation to deal with. Again, we know that x squared plus y squared is something. It's in fact r squared. And then we've got 6 times x minus 2 times y. But I know that x is r times the cosine of theta. And I know that y is r times the sine of theta. Okay? So we'll notice now that we've got 3 terms, 1 on the left side, 2 on the right side, but they all have r in them. So what if we just divide everything by r? Whoops. What if we divide everything by r? So we get r on the left side. We get 6 cosine of theta minus 2 sine of theta. And that's a really slick way of getting rid of that extra factor of r on the right side. And look at that. We're done. We've solved for r in terms of theta. So that's a nice way to convert this circle into polar form.